Okay, so we're going to be doing a live coding session. Some of you saw Jonathan do one of these in track B. And we're going to be working with the model that was worked. Okay, so Julie, do you want to tell us about the model?
So this morning in track B, we created a model world to address a research question. So we are working on formulating questions that can be addressed by dynamical models and then creating models to address them. The example that we used this morning was the question of what level of vaccination is needed to eliminate domestic dog rabies in Tanzania. And we came up with a model world to address this question. Our model world has 4 types of individuals: susceptible dogs, exposed but not yet infectious dogs, dogs that are infectious and symptomatic, and dogs that have been vaccinated and therefore are protected against infection. And the individuals, so we're only modeling dogs, the individuals in our population can move between these different compartments through a number of processes and into and out of the population as well. So there's two processes that bring dogs into the population. One is birth, which introduces susceptible dogs. The other is importation of infected dog cases. We're calling it importation, but it's basically any time that a rabid dog shows up from outside of the area. And that may be partially due to wildlife or movement of dogs. We have basic demographics, so I mentioned the birth rate. We also have a background mortality rate. All of the different compartments experience the background mortality rate. And then we have a number of transitions between the compartments that can occur. So obviously we have infection. So infection occurs when a susceptible dog bites, an infected dog bites, an infectious dog bites a susceptible dog. So you can transition from susceptible to exposed. And there's a force of infection that's proportional to the proportion of infectious individuals in the population. And then exposed dogs can become infectious and symptomatic. Those dogs experience an elevated death rate, so we have alpha I, which is the disease-induced mortality rate. And then, as I mentioned before, we have a vaccination process. So our research question is what level of vaccination is needed to eliminate domestic dog rabies in Tanzania. We need to have vaccination in our model. And that process I have denoted with a little lightning bolt. Because unlike the other flows, which are continuous processes, vaccination is occurring annually. And so we have a pulse that occurs all at once. We want to represent this realistic feature of the vaccination process in the model because we think it's important. And so we actually are sort of conceiving of this as a proportion of individuals that are vaccinated, and that's our question. Our question is really what proportion need to be vaccinated every year in order to maintain the level of coverage that's going to allow rabies elimination. But we also sort of have incorporated conceptually into our model the fact that the proportion successfully vaccinated is going to be less. So we have a vaccine efficacy and a proportion that we vaccinate to get a proportion successfully vaccinated, and that's how that transition arrow from S to V is labeled. Are there any questions about the model world before we move on?
Yeah, later. I don't know why we have dotted lines going back from the I to the.
Very good question. So this is our convention that we use at ICI 3D. So all of the solid arrows are transitions into or out of a compartment. The dashed arrow is representing the fact that that rate of transition depends on the value of one of the state variables. And it's not the variable that the arrow is coming out of, but it's another one. So if you look down in the bottom right-hand corner, we have a derived quantity called the force of infection, beta I over n. So that dashed arrow is just a big reminder, should be a big reminder that the rate of flow from susceptible to exposed is dependent on the current number of individuals in the infectious compartment. Thanks for that question. Any other questions? Jeremy?
Could you explain the graph on the bottom left?
Sure, I'll try to. So the graph on the bottom left, that's your proportion vaccinated on the y-axis and time on the x-axis. And it's really just trying to represent that this is a process where there's a pulse. So it's not continuous vaccination. As dogs are born, they're getting vaccinated on a regular time scale. It's that dogs come into the population all year long, but then once a year, a vaccination team goes to the area and vaccinates some given proportion of the dogs. And so that's an attempt to represent that. Other questions? So we need to understand this model world, because what we're going to do in this session is take this model world and translate it into some code and actually write down and run a model. So if there are any other questions about the model world, we want to get them out of the way now so that we can move on to this next step. I've also written the basic structure over here because we're not going to be able to look at this the whole time.
Sorry, Catherine. Sorry to mention about the lightning bolt.
Yeah, the lightning bolt is just my attempt at denoting the fact that that flow from S to V is not a continuous process.
All right, I think let's get started coding it. Okay, okay, looks good. Okay, so here's our code to start with. We're starting from blank code. I'm going to start R. First of all, I should say this is R, so it looks different from RStudio because I use a different text editor instead of RStudio to run R, but it's the same. I happen to like this black with green, so it feels like I live in the Matrix. Okay, so I'm going to have R on the bottom some of the time, and then this rabies code up here. Okay, so the first thing we're going to do is, rather than start from scratch, is I'm actually going to say, I don't want to waste time reinventing the wheel. I'm just going to copy the code from Lab 1, the OD model, so I can have all the L soda and just all the syntax, basically, and start from there and edit it. And that's what you should generally try to do. You can use our tutorials to start your own models. So I've already taken a streamlined version of that, and can everybody see the code pretty well? I'm going to make it a little smaller. Can people still read? Yeah? Okay. So the first thing, we're going to run dsolve. And now we have an SIR model here, right? So the way this works is we need to give it a time point, a vector of state variables, and our parameters. And then, if you recall, we can run it down here to get time series output. This is what you did in Lab 1. And so we're going to now start to modify this, make it full screen, to look like the model that we're working with. So what do we need to add? Right here we just have S and I. What else? What's missing so far? E? Okay, so let's add E. So D, E, dt. And I know that this now needs to go into E, right? Because first infected individuals are going into the exposed category. And what else do I need to do? They need to leave E, so the rate at which they're leaving E, we're calling sigma, right? E, okay, great. What else is going into S? Birth, okay, so we called that new. I'm going to actually say, let's just call that births. Okay, why don't we make this more readable, okay? And even over here, I'm going to say, let's call this progression. Thank you. Okay, progression rate, and this is births because it's not a rate. It's actually, well, it's the total birth rate. Total birth rate, and then beta. What else is going into or out of S? Yell louder. Vaccination. Okay, so we need vaccination rate times S. Okay. Anything else? Deaths. So minus natural death rate times S. Okay, so that seems like everything. Okay, E, is there anything we're missing? Deaths, right? So, okay, so now we have that. What about I? What else is happening with I? Well, first of all, we need to actually make sure the people that are progressing from E go into I, right? Oh, did I? Thank you. Oop. Okay, what else is going on with I? Into or out of I? Is that it? Okay, so minus rabies death rate. They're also dying of natural death, right? So let's put that together just to remind ourselves that those are the two deaths, right? Okay, so now we've got both the death rates. Anything else with I?
Outside
Importations? So I'm saying total for things that aren't being multiplied by other state variables in the system, just to remind myself that this isn't births per individual, this is the total births per unit time, whereas every other rate we're multiplying by a state variable. Okay, just to keep that straight. Anything else missing in this model? V, okay, so dV, dt. So where are the people or the dogs in V coming from? S, okay, so it's this, okay, and they're also leaving through natural death, okay? So we also now need to make sure we're spitting out what we need to down here, so we're going to add all the derivatives here, and now it looks like I think we have everything. Is there anything anybody's noticing I'm missing?
Steve,
Yeah.
Invention question. Why are you choosing a second word that's actually ready to capitalize the second word?
Just so it's easier to read. Yeah. Yeah. And you don't have to write it with these words, but it's often easier. And as you can see, I'm auto-completing the code, so if it's a long word, it's not difficult for me to write it. So it's better to make code readable as much as possible because then you can find errors. Any other questions or notes? Yes?
I was just wondering, so comparing this to the SAR model, we had not specified DRDT that's left over in the notes, and I was wondering why, so here we're specifying all four, so are we not making the same assumption about population size staying constant?
You're right, we're not. Yeah, because we actually do have, we haven't defined the birth rate yet. So we could define the birth rate to equal the natural death rate plus the rabies death rate, and that would be a way to keep it constant. And so we're going to have to decide if that's what we want to do. But it may be tricky to do that. Maybe we don't want to do that. So I'm going to delete that for now, and we'll see what happens. And we might come back to that, because that's something that often will trip you up. If you have a growing population or a declining population in your model, and you just look at I over time, it may look like it's declining just because your population's going extinct, because the death rate's much bigger than the birth rate, for instance. Yes?
Importations going into infections versus exposed, being exposed.
That's a good point. Maybe the animals that are coming in aren't crazy rabid yet. They're just infected. We could have done it differently. We could have had dogs coming in all the time into any of the compartments and just think of a proportion of them that are actually infected. That would be another way to do it. I guess this is a simplifying way to do it that is giving us maybe what we want, which is just that there's always going to be some rate of introduction. So even if it goes extinct in this population, it'll seed back up again. But certainly, this is a bit of a weird way to do it, where the only dogs that come into the population are already rabid. But it is also true that rabid dogs maybe wander a little bit more than non-rabid dogs. Other questions or points? Yes?
In the equation of DIDT, what is the unit of total importation rate?
So everything on the left is the derivative of dogs with respect to time. So every component part of it must also have that unit. So total importation rate is number of dogs per unit time. And if we wanted to make it specific, it's number of infected dogs per unit time. So that's the unit of it. So you're thinking about the number of infected dogs per unit time coming in. Whereas, again, for instance, when we're looking at this parameter over here, the natural death rate, this is deaths per dog per unit time. So there's also a per dog in the denominator, which is why we have to multiply it by S to make it dogs per unit time. Again, units. If you can always double check that your equation makes sense with respect to units, you'll avoid a lot of tricky errors. Okay, so why don't we move on and see if we can try to simulate this model now and get some output. Okay, so I'm going to relabel it. So how big is our population size? Anybody? We're talking about Tanzania. Whoever, I'm going to be asking for a lot of parameters, so this is your chance to put your stamp on this model. Whoever yells a number first gets to have that number in there. How many dogs?
5 million.
5 million. Okay. Okay, we got 5 million dogs. Okay. So we need to start with some initial conditions, okay? Which means we need to have a S that we start with, an E that we start with, an I that we start with, and a V that we start with, right? So what proportion of the dog population at the starting time do we want to be in each of these compartments? Again, here's your opportunity. How many dogs are susceptible at the beginning of time? Do we want all of them to be susceptible, or 5%? 90%. First number wins. Okay, so the other 10%, where do we want to put them? Do we want to put them in the vaccinated category, have them all start rabid, have them start on their way to becoming rabid? All vaccinated, okay. So that means we're left with 0 dogs infected, okay? In a model that doesn't have importations, that would give a pretty boring result, right? If there wasn't any dog infected at all, we just wouldn't ever see an outbreak. But because we do have this importation, we can be pretty certain already that there's going to be infected dogs coming in. Might not cause an outbreak, but we know there's infected dogs coming in the model if we set that parameter to be above 0. Okay, so we now have our initial conditions. We now have to give some parameters, okay? So we have beta, the transmission coefficient. What do we want that to be? First of all, what are the units of that? So what does beta have to be to make this whole thing, sorry, not that whole thing, this whole thing be in units of dogs per day? One over a day, correct, right? Because I over n is a proportion, it's unitless. And so beta times S has to be dogs per day, so beta has to be per day. So what does it mean that beta is per day? What is beta? Number of contacts, right? So this is the frequency of contacts, right? So rates can just be inverse time. The frequency of contacts is going to be 1 over a day. So how many bites do we think a rabid dog is making per day? On average? 10 bites. Great. Okay. So other things. Let's just go from the start of the equations to the end. So we have total birth rate. Okay. Do we want to set that here? Or do we want a constant population size? This is our chance to make that decision. Let's set it here. Okay. So total birth rate.
Remember, you can always change it later.
Yeah, you can change it later. So how many dogs are coming in per day to this population of 5 million dogs? Or tell me in years and we'll convert it to days. 5,000 dogs per day, okay? So 5,000 dogs per day are being born in this population. Next parameter is the vaccination rate. So Julie wrote her model as having that lightning bolt pulse, which meant we were going to have the vaccination happen at one specific time. We're going to try to do that within this session, but first we're going to have a constant vaccination rate to keep it simple and see if we can get there and then do the pulse one. So the vaccination rate, what do we want that to be?
1,000.
What's that?
1,000.
1,000 per day? Or 1,000 dogs per day?
1,000 dogs.
1,000 dogs per day, okay. But we're multiplying the vaccination rate by the total number of dogs that are susceptible. So we actually don't get to decide the dogs per day that are vaccinated. We get to decide the vaccination rate per dog per day, right? So another way to think about this is the average amount of time a dog spends susceptible before it gets vaccinated, right? Because we said that the rate of flow out of a compartment is equal to the average of the rate of the amount of time it spends in the compartment. So maybe let's think about it that way. How long do we want a dog to, on average, spend susceptible after it's born before it gets vaccinated?
100 days.
Sorry?
100 days.
100 days, okay? So if we do 1 over 100 here, then that's going to be 1 over day, equivalent to 100 days susceptible before vaccination. Okay. Okay. Next parameter is the natural death rate. So the units of this is what? Per dog per day, right? So so again, the inverse of this is equivalent to what? Life expectancy. So how long do we think a dog should live if it's dying of natural death?
In Tanzania. In Tanzania, right?
Yeah, in Tanzania. 3 years? Okay.
We have an expert in the room, actually.
Nobody told us this morning it was 2.5 years, I think.
Yeah.
Okay, so the expert's opinion superseded the first person. Okay. Okay, next parameter, progression rate. 1 over that is equivalent to what? The amount of time you spend in E, which is the latent period. Okay, what is the latent period for rabies? What, you said it first?
No, if I remember, it was 20 days or something like that from the paper.
Okay, so let's go with 20 days. Okay, next parameter is rabies death rate. How are we going to get that parameter? What's the easiest way to think about that?
How many days it takes a dog to die?
Yeah, if it's infectious, how long does it live before it dies?
2 days?
10 days.
2 days? 10 days?
3 days.
Do we have a consensus?
No?
Expert opinion.
It's 10 to 14 days. Let's take 10.
10 to 14 days?
Does anyone remember from the Tanzania paper that you read last week?
So I think, isn't 10 to 14 is how long from when they start, from symptoms to death? Okay. You're the expert, so we'll say, I believe, let's see, infectious period. So we can delete that line, And what do we have next? What's our next parameter? Total importation rate. And again, what are the units of this one? Dogs per day. Okay. And how many infected dogs per day do we want coming into this dog city of 5 million? 50? Okay. Let's start with 50 and see what happens. Seems like a lot to me too, but yeah, it's a big dog city. Okay.
Does it come from other animals, or is it just an importation of a rabies? Like it could come from a wild animal?
Yeah, it could be. We could be thinking about it that way. We're adding infected dog to the system that wasn't previously susceptible dog. So it's not as if like a jackal or hyena bit a dog in the way we're modeling it, because it would be a bit a dog that then came to the city, which may be reasonable if we're thinking that the wildlife aren't actually coming into the city and biting dogs in the country that are then wandering into the city. That might be more consistent with how we're modeling it. If you wanted to model it in terms of wildlife biting dogs, you might do it by having the transmission rate that causes S to go into E to be affected not only by the number of infected dogs, but also some constant parameter. So that might be more consistent with that mechanism. Okay, so anything else? Yes, Becky?
So we can go with this and see what happens, but I checked the Hampson paper and mean duration of infections period was 3 days.
3 days. Okay. So should we start with 12 days? And then we can do a sensitivity analysis. Okay. So I think we have most of the things we need.
Is that because a lot of dogs would probably be killed before they could
Yeah.
go all the way to 10 days?
Biologically, it's about 10 days. Practically, it can be less because of intervention.
Okay, so that might be an important difference that explains that. Great. How long do we want to run this model for? How many days? 2? A billion? A trillion? A year. Okay, so we've already got a year. This is days. I'm going to be really good and say per day here, per day, or this is per dog per day, right? Wait, natural death rate? Yeah, wait, per day. Okay. Okay, so per day, good. All right. So let's run this and see what happens. So I'm going to split it into 2 panels again so we can see. Let's make this a little smaller. All right, let's see if we can run it. Okay, so a bug because we changed the name of the model. Okay, looks like we ran our new group model of rabies in Tanzania. Before I plot it, the first thing I always do is look at a new data frame object and see what it looks like. Okay, so we have this object, SEIV. Does it look like the epidemic is taking off? It does, right? We can see pretty clearly that I is increasing. So what do we want to plot to start with? I, okay, which we already have here. So time in days. Let's change the label so it's appropriate. And I think I should be red. not just because it's my favorite color. Everybody ready? Is there suspense? We got an epidemic. It's a big one, right? Okay, what do people want to do now? Like what? So what was our research question? All right, let's go back to that. What do we want to know? What level of vaccination is necessary for elimination? Okay, so we put in vaccination here, but we haven't looked at it without vaccination. So maybe we should actually run this model with and without vaccination to see what the effect is. And I'm going to say, I kind of see that red line looks like it's going up again. Does anybody agree with me? No. Nobody does? Well, I'm going to use my power up here to say, let's actually test that first by running it for 20 years, okay? Okay. I stand corrected. It was worth checking though, right? So now we can...
It goes past it, right, and then comes up a little bit. I stand by both.
The tail... Oh yeah, thanks. So we looked at the start of the data, but let's look at the end of the data. So what's going on here? Did we eliminate rabies? No. How many dogs are rabid? 53,000 dogs are rabid in this city, right? So I don't think our vaccination efforts have worked yet, okay? Yes, Jeremy.
Would we consider our vaccination efforts to have worked if we had just one peak and then it die out? Are we happy to let there just be 1 million rabid dogs for a little while as long as it dies out?
What do you think?
I mean, I don't live there, so. It doesn't seem great.
Yeah, so maybe not ideal. So maybe we want the vaccination to prevent an outbreak in the first place. Okay, so
or maybe our starting conditions are really wildly inaccurate.
Yeah.
So we might want to think about that also before we think too much about it or not.
yes, Kristen.
Is there a way to model how the number of dogs vaccinated would influence the actual path from susceptible to exposed? Does that make sense via like herd immunity or something like that, or does that not really make sense?
So we are modeling herd immunity. Herd immunity is the protective effect that a susceptible dog gets because R effective is less than R naught, because the susceptible proportion is smaller because some animals are immune. And that's built into this model, right?
It doesn't have to kind of come back.
It's not something we put in as like, this is herd immunity. Actually, that's the reason we build these models is because herd immunity comes out of these simple assumptions of saying the rate at which animals get infected is proportional to the number that are infected, but they have to come out of the susceptible compartment. And so if there aren't many animals susceptible, you don't get many infected, which then means there aren't many to infect. And so it's this feedback loop of vaccination. By removing them from susceptible, we reduce I, which reduces the flow into I. Good question. Okay, so I'm going to say I'd actually like to see some other lines on that plot. Right? Remember in that first lecture that I gave, we don't always want to just look at the eye, right? The stuff that's going on in the background is what's affecting the eye, like we just talked about. So let's at least add some of the other lines.
While you're doing that, Becky is pulling up the Hampson paper. So we maybe could make some more parameter values.
Okay, great. So let's look at the number vaccinated and make that blue. And since some people are in the back, I'm going to make all the line widths a little thicker. So what's going on with the number of dogs that are vaccinated? Maybe we should. Kari.
It's one small mistake. I don't know how much the difference is making, but you use the total population size, but you don't. Oh, sorry, is that something the participants should have noticed?
You mean, well, so we're going in that direction. So remember we said, let's guess the birth rate and let's go back to it. Okay, so we don't have a constant population size, right? As both Kari and Julie just suggested, maybe we should actually look at that. Okay, so let's just do a simple plot of that. Did I do this right? I don't think I did. Do we have, so we don't have a variable called n, so I'm not actually sure what R is doing. So I'm going to say we're going to define n right over here anytime we do this. N is going to be equal to my TS of S plus E plus I plus V. Okay? Now we have an N. Aha, let's make it a line. Okay. Are my axes labels big enough? I don't think they are. Since I've been hammering about that, I'm going to make sure they are. Is that better? Okay. So what's going on with our dog population over time?
They'll die.
They are getting decimated, right? So let's go back to the, well, actually, I like having this model of 20 years. Okay, I'm not going to turn it back to 1 year. But after 20 years, our population has dropped from 5 million dogs to 1 million dogs. Right? That's, what's that?
Good population control.
But so why is that happening? Did we put population control in the model? What did we do in the model that made this happen?
Natural death rate is too high.
Maybe the natural death rate is too high. Or, alternatively, another way of looking at it might be the birth rate's too low. Yeah, right? So maybe we want to make this a constant population model, right? Maybe we want to say if the births coming in were equivalent to the dogs dying of natural death and rabies, would we be able to eliminate rabies? So we're not confusing whatever patterns are going on with the disease with some demographic patterns that have to do with our poor understanding of what is going on with this population over time.
Or alternatively, we could use a birth rate that's more realistic that we actually have from kids again.
Sure. Shall we do that? All right. So let's give me some birth rates, Becky.
It's a little bit complicated. I have parameters for the litter size, pup survival, litter frequency. I don't know if there's an actual birth rate. I have a death rate.
Litter size and litter frequency, I think, can give us a birth rate.
Yeah.
So
you just want all of those numbers?
yeah. So what's litter size?
Litter size is approximately 5.
5 and frequency?
Frequency is 0.84 for female dogs greater than 3 months.
Per year.
Per year.
Per year, yeah.
Okay, so let's see if I can do this right. So we have 5 2.5 divided by 2, because male dogs don't give birth as far as I know, times a frequency of 0.84 per year, but we got to divide by 365 because we're talking about days. Does that seem right?
Which is 5? Which is
35 million.
5 million.
But we're multiplying. Oh, this is total, right? Okay, so if we have so maybe we don't want it. Do we want to do a per capita birth rate?
Which is 5?
Yeah?
Well, let's see what that is to see how far off.
All right, so let's look at this first. So now we have 28,000 dogs
So
being.
there's an additional parameter that might be informative. Pup survival at 3 months is only 0.31 dogs per year. So 1 out of every 3 dogs in a litter dies.
Okay. And maybe we don't think those dogs are playing a big role in the rabies transmission cycle, and we can ignore two-thirds of the dogs that are being born. Okay, so let's. Yes?
Can you explain us what is 5 and why divide it by 2?
Yes. So Becky said that the average litter size for a female dog that gives birth is 5 pups. But I want to know how many dogs each dog on average has in a litter. So I need to divide by 2 because male dogs don't give birth. Right? So the average litter size per all dog is basically 2.5. But we also need to know the frequency, and the frequency is 0.84 per year. So that means these female dogs aren't giving birth every year, a little bit less than every year. And so, no. So maybe the better way to think about it is 5 dogs every 1 over 0.84 years is what we're getting. So the rate at which dogs are being born per female dogs is 5 times 0.84. And then the rate per all dogs is 5 times 0.84 divided by 2.
Yeah.
So let's write it that way. And then, so we have survival rate of 1/3 for pups. So now we have 9,000 dogs being born per day. Okay, so a little bit more than we had before. Let's see what we get. Let's just look at our population size to start with. Seems like it's still going down, but maybe, oh, it didn't finish running. I'm going to also say that I don't like those axes not going down all the way to 0. It's misleading. Remember what Jim said about the ranges, right? Let's make sure that we are going all the way up and all the way down. Okay. So it looks like we're still having a crashing dog population that's reaching equilibrium now at maybe about 800,000 dogs. So you can see it's kind of tricky to balance the birth and death rate in models where you think you have estimates of one and maybe the other, but if they don't totally match and you run a simulation over a long time period, you're going to have the population re-equilibrate to what the birth, when the birth and the death rate are equivalent. So
remember that we made up that 5 million number, so now we could go back and adjust our initial position to be consistent.
800,000.
Yeah, to be consistent with the birth and death rates.
All right, shall we? Okay. All right, so let's make N naught now 720,000. Okay. What's going on here? Still waiting for it to finish. No, that's right. It still is crashing. Is that right?
So what's the final?
It's ending up at 102,000 dogs. Now. We might just have. Let's see what happens. I don't think I redid this. It's part of the problem. So let's go back to that. Still going 100,000 dogs. What? No, it's going to 700.
So, very minor point. You still have n equals n naught in the base setting of parameters, but n is variable, it's not constant. But yeah, so it's what gets used in the model is that n from values.
So that is correct, right? Yeah, so we need to fix that. We need to put n is equal to s plus e plus I plus v in here. And be a little more careful. Thank you. That could have been part of the problem. Okay, so let's run this. Let's do that. And I don't think we even really need that in there because it's not being used. But let's leave it in. Sorry? So we still seem to have a population of dogs crashing. Our natural death rate is 1 every 2.5 years, and we have a total birth rate that is, at this point, for the purpose of this lecture, I'm going to say let's do a constant population size instead of trying to balance this, so that we can ignore this dog demography, and we can still change the turnover and keep a constant population size. But you can see how this can be tricky if when you decide to have one be per capita and one be constant. So
can you check this version in somewhere so that we can go back and diagnose it?
yes. Okay, so what we'll do is we'll make the total birth rate equal to all the deaths. Okay, so total birth rate is going to equal natural death rate times S plus E plus I plus V plus what? Rabies death rate times I. Is that it? There's one more thing. That's very minor, but there's one other way animals are flowing into this model, which isn't birth, importation, right? So if we want it to be constant, we actually need to subtract the importation rate. And that way, we'll have everything balanced out. Okay, so now we've defined, before we put the total birth rate in there, just a function of all the other flows in the model to make sure everything's balanced out. And again, we can still change the total importation rate, and we can still change the natural death rate, so we can affect the demography within the model, but it's going to be balanced. The dog population size is going to be constant. Okay, so we don't need this parameter in here anymore, so I'm just going to comment it out because we're calculating it within the system of ODEs. Okay, so we start with 100,000 dogs. Sure enough, we end up with 100,000 dogs, right? It's a nice quick fix to make sure we're not having this dog population going up or going down. So always, especially when you have complicated birth and death rates, check the population size before you start looking at other curves. Okay, so now let's look at the stuff we were actually interested in. Let's put a legend on here so everybody's on the same page. So bottom left. So we're showing infected, or let's call them rabid dogs, and vaccinated dogs. And what do I have going on? Okay, meant to make it on the bottom right. Sorry. But, so what's going on now? Are we getting an epidemic? So have we eliminated it with this vaccination rate? Okay, maybe let's go back to looking at just a few years. Okay, and we can see we vaccinated dogs, but the number of rabid dogs has still reached a fairly high equilibrium based on this. And we probably need a higher vaccination rate. So why don't we do a sensitivity analysis where we look at the trajectories for a bunch of different vaccination rates. Okay, so we said we are vaccinating dogs on average after 100 days, I think. So maybe let's see how that parameter affects things. Okay? Any questions? Yes?
Sorry. When we're writing the formula for total birth rates, is it a must that we put it into right there in the function, or could we have done it later when we're writing all of the other values?
We have to do it inside the function because it's something that's changing as a function of S, E, I, and V. So if we do it out, anything that's changing as a function of the state variables in the system has to be in the differential equation part of it, because it's not a parameter, it's not constant. Okay, so let's do, I'm going to create a new function that says do run, and it's going to be a function of vax rate. Okay, and what it's going to do is what we just did down here, and it's going to spit out, oops. So I don't have to run all the lines of code. What I want it to do is to say take values and assign the vaccination rate in that to be vax rate. So I can now run this simple, well, this one line of code that is going to vary the vax rate. So if I do it with 50, that's going to be a very high vaccination rate, right? That means dogs are vaccinated instantly. Okay? So let's say my TS of instant dog vaccination. Hopefully that should eliminate rabies, right? If we're vaccinating dogs within a 50th of a day, that means right after they're given born, all of them. Okay? So let's see, is it not looking good? So after a couple years, we still seem to have 600 dogs that are rabid. Why do you think that might be? The importation rate, right? Remember, we set that as super high, right? 50 dogs per day are coming into the system rabid, and they each live for how long? 12 days. So on a given day, if 50 dogs are coming in per day, that means we should expect about 50 times 12 dogs to be rabid, right? Which is about 600 dogs. Sure enough, we've vaccinated every dog that's being born, but we have an importation rate that's so high that we're always going to have 600 dogs that are rabid in the system, right? So clearly, we need to change the importation rate to be something a little lower if we expect to ever get lower than that. So maybe we want to fiddle with that parameter a little bit now.
We could also make sure that our beta and our parameter is more.
Right. So our beta, we're saying each rabid dog is biting 10 times per day. And we're saying they live for about 12 days. What's R naught roughly? Right? So each dog's biting about 10 per day for 10 days. Each dog on average is biting 120 other dogs before they get killed. Does that seem realistic? Okay. It's not. But actually what's going on in this system is that doesn't matter because every other dog is vaccinated because we vaccinated them instantly, okay? So this is, part of this whole process is to like think through all these assumptions. Are we making realistic assumptions, okay? So what do we want to change first to make this more realistic?
Infectious fever?
Importation rate, okay, so what do we think is a more realistic importation rate?
Or infectious fever?
2, 1. I'm going to say, let's say there's only a rabid dog coming into this city once every 30 days. How about once a month? Okay, and let's see if that can spark an outbreak. It seems a little crazy to me to think of a city where there are just all these rabid dogs. like it's a vacuum for rabid dogs. I don't know of too many cities like that. Let's try one per month. Okay, what about beta and... Sure. Okay, let's see what reducing the total importation rate does. And let's do it back with our 1 over 100. And just so it's clear what this is, vax rate. Okay. So it looks like we still have quite a lot of, thanks. Okay, so we're getting it taking off. It doesn't look like it's happening as quickly. It seems like we're winding up with some dogs. Let's see what it looks like. So we're still getting a pretty big epidemic.
But remember, this is with the
This is with R. This is also with R naught still at 100.
Yeah, yeah, but it's also with full vaccination rate, which is transferred.
1 over 100.
The original one, not the 50.
Right. So now let's try changing R naught, right? So it's not 120. So how do we want to do that?
Infectious period.
Decrease the death, the baby's death rate.
So the infectious period and decrease the death rate, the same suggestion, two sides of the same coin. So let's go with the Tanzania paper, which Becky said it was
3 on average.
an average of 3. Okay, so now our R naught is approximately what? 30, right? So it's still pretty high. Should we run it and just see what happens before we try to fix that? Still getting big epidemics. Shouldn't be too much of a surprise. What happened to the vaccinated dogs? Did they disappear? They were what? They might be up, right? We set our axis to be by default based on the number of infecteds, and so we actually can't see it. So let's fix that. Now we can see it. Okay, so this is what's going on. So we're still getting a pretty big epidemic that's equilibrating at about 8,000 rabid dogs, which is still a city I don't want to live in. But we have a lot of vaccinated dogs. We haven't looked at S this whole time, right? Maybe we should start looking at that a little bit too. What color should S be? Oh, legend. Let's move that to the top. Okay. So the susceptible gives us a much better picture of what's going on, right? And we now see that the dog population is crashing due to 2 things. The dogs are getting infected and we're vaccinating them, right? Okay, so what's the next thing we want to change to make this a little more realistic? What is still beta, right? So Becky, in that paper, what do they say, what are their estimates for R naught around for rabies?
R naught secondary cases 1.14.
So R naught for rabies, at least from this paper in Tanzania, is about 1.4. So if a dog is infectious for 3 days, it's only biting 1.4 in those 3 days. So what do we need to set beta to be for R naught to be approximately 1.4? 0.5, right? And we can actually say
So it's actually 1.14, but I don't know. Here.
that's okay. Let's go with 1.5. Okay, so so now we can kind of run this and we actually have a way to just check our R naught. Now this is not the exact calculation for R naught, right? We showed that when we have an SEI model, we have to calculate the proportion of dogs that after they get bitten don't get hit by a car while they're in the E class, the latent period, right? And they also could let's see, is there anything else in this model that's affecting that? I think that's the main thing that, well, the infected dogs can also get hit by a car, which shortens how long they're infected. But this is pretty close, right? We said that the main thing is how long they're infectious for and how long they're biting for. So now we have something that's a little bit more realistic based on the data that we know are out there. So let's now simulate that. Okay, so now what's going on? We're not even getting an epidemic, it looks like. All right, we saved the world. We eliminated rabies. Well done, everybody. So, but really, what does this mean? So I, at the end of time, is down to 0.1 dogs, right? So just like a rabid dog foot or something like that is floating around the city. So maybe this vaccination rate is sufficient, at least with these parameters. So maybe, but vaccinating all dogs within 100 days of birth is maybe a little bit fast, and maybe that's really expensive to do, right? So maybe let's see how infrequently we can vaccinate dogs to actually get elimination.
Or maybe before we do that, maybe we could think about what's a realistic sort of approximation here. So if we're going to have annual vaccination campaigns, what does that mean on average, assuming there's no major seasonality in dog birth rates? What does that mean on average for how long it's going to be? The dog is in the population before it gets vaccinated. Half a year. Yeah, so we're trying to.
So half a year, so that's going to be right? Did I do that right? Well, 1 over 365 would be every year.
Yeah, 1 over 365. That would be a dog would on average be there for a year before being vaccinated.
Right. And so we're talking about every 180 days.
Yeah.
Let's do that. Okay. All right. So it seems like that campaign is also maybe good enough to eliminate rabies from the system.
Is that assuming 100% of the dogs are vaccinated?
It's actually assuming that all dogs are on their way to getting vaccinated, but on average they spend 6 months unvaccinated before it happens. But it's not the same as saying all dogs are vaccinated. There's a rate at which we're moving them to the vaccinated category. Yes?
Could we please run it when vaccination is at 0?
Sorry?
Could we please run it when vaccination is at 0? Vaccination rate is at
Great
0.
idea. So let's look at what happens when we don't vaccinate any dogs. So what's happening here? So we're getting an epidemic. It's reaching equilibrium. It's a slow epidemic because we don't have these dogs biting 100 dogs. And we have no dogs getting vaccinated, but we started with 10% of them vaccinated from, I guess, people were vaccinating dogs and then we're modeling it where they stopped. So the susceptible declines because there's an outbreak. So if we don't vaccinate, we are winding up with, it looks like, something like about 4,000 dogs out of 1 million that are rabid at equilibrium. Yes?
Jeremy, might it be realistic to have a constant vaccination number? Because the government probably has a certain amount of resources that they can put in, which probably corresponds to a certain number of vaccines, not a proportion of the population.
Mm-hmm. Yeah, so we could say that that there's a certain number of dogs that we're able to vaccinate per year.
So, but in order to do that, we want to move more towards this framework, because we could also say that there's a total rate at which dogs get vaccinated, but if we do that, then we might end up trying to vaccinate dogs that aren't actually there. So if we say we're going to vaccinate 1,000 susceptible dogs every day, for example, and then the susceptible dogs goes very low, then we would end up taking dogs and our model would break because we'd end up with negative numbers. So we can't do it that way. So I think that would be an appropriate time to start shifting towards a different approach to the implementation of vaccination in the model.
So I'm going to see if we can get to that. I don't know if we actually have time, but before we do that, let's do a sensitivity analysis to this vaccination rate thing. Let's figure out how frequently we need to vaccinate to actually get the epidemic to be eliminated. Because we've looked at it when there is an epidemic. We've seen that for vaccination on average after an animal is 6 months old, that seems to eliminate it. Let's figure out where we have to go. So to do that, I'm now going to write some new code down here, sensitivity analysis. And I'm going to, for vaccination rates, a sequence of vaccination rates from, let's say, 0 up to, let's see, the fastest vaccination, well, we know at 1/180 is going to eliminate it, right? So maybe let's look at annual. Let's go up to 1/180, because we know that that's going to be sufficient. And we'll do a 100 values in that sequence. Okay, so what is this? What did I call it? Vax rate. Okay, so what is this? This is all the different vaccination rates we're going to try. Okay, and maybe it's easier to read it like this. How long on average in days an animal spends until it gets vaccinated? And we're starting at basically it never gets vaccinated, all the way up to it gets vaccinated within six months on average. Okay, and we're going to try those out and see what it does. Okay, so we have this. So for this, for each of the values in this sequence, we're going to run this function. And we're going to run it, and then we're just going to collect the number infected at the last point in time. Right? Because that's what we want to know. We want to know how many are infected after, what are we running it for? 2 years now? 5 years? That should be good enough. So after 5 years, how many dogs are infected? So my TS, let's even do it, plus E. So how many dogs are actually infected, even if they're exposed? And we're going to say final infected is that. And we're going to create a new sequence that's going to be final infected sequence, which is going to be an empty vector that is length of this. So for each of these, we're going to be filling in one of those with how many dogs are infected at the end of time, and then we're going to plot it. So what I'm actually going to do is I'm going to do this with better syntax. So I'm going to say from 1 to the length of this sequence. Let's do it this way. Seq length okay, so we are setting everything to be seq length long. And so for a for loop in that, we're going to run the SEIV model calculate the final number infected by going to look at only the last number, right, using the tail, right? If I do tail of 1 through 10, and I ask for the last 3 values, it gives me that. 1 gives me the last value, so that's what we're doing. And then we're going to set the VETH value of those NAs to be final inf. And we're going to nicely give ourselves updates to say what we're doing.
Can anyone tell us why it's not going to work? Catherine?
Yeah, backstory is always going to be 0. When you do runs, you want to set that to be the brief value of your backstory speed.
Thank you.
But in the meantime, we've run it, we can verify.
So let's look and see what happened. Yep, it all is the same because of the bug. It's easier to catch bugs when you have 50 people watching you code. Okay, so I forgot an S again. Okay, and while it's running, I'm going to start the plot because I know what I want to plot. I want to plot vax rate sequence versus final infected sequence. And I want to label the axes. Vaccination rate and final number exposed infected. All right, so what have we learned? What should I, remember the visualization lecture? Don't present confusing plots if you can avoid it. How can I make this plot easier to understand? What was that? What is the vaccination rate? Right? It's this confusing thing that we only understand as 1 over the amount of time a dog spends susceptible before it's vaccinated. So why don't we just plot it versus that instead? Easy enough. Okay. Let's make it in terms of years, even better. And I didn't label the units, now I will. So it looks like in this model, if we vaccinate dogs within 5 years on average, that seems to be good enough.
They're not living that long. Yeah.
On average, they're not living that long. So,
You don't need vaccination.
well, if we don't have vaccination, what happens? Wait, if we don't have vaccination, we have 25,000 dogs, right? It's approaching this quite large number. So actually, what we're seeing is that's very sensitive to vaccination, but we don't need a lot of it. Yes?
I thought we went only until 180 days. Where's the 50 years coming from?
Yeah, I think there's something funny.
Okay. So that's right. So, okay, so what's going on? Help me catch the bug. So,
Days, just see the days first.
okay. So we went up to 180 days. Oh. on the
I
back.
think we want to go from, so we're going from infinite to 180.
So we just set at 1.
So we should. So
Do
these
you
are
want to
really.
reverse your
Still gonna look. I mean, we could change the axis, but it should be. So 180 was enough. I think this is still consistent. I think this is right. But Julie points out that maybe we want to reverse the direction of the x-axis to make it a little bit more intelligible. So let's go from like, what are we, 5,000. Okay, so again, you're free to make x-axis start at higher numbers, which I think in this case, to me, makes more sense, because as we move to the right, we're increasing vaccination. That's how I like to think, at least. But it looks like if we get to about 1 every, what is that? So again, we could convert it to years, but basically, we're very close to being able to eliminate this disease through vaccination. Let's see, R naught is 1.5, so we should only need to have 1/3 of the dogs be vaccinated to eliminate the disease, right? Because R naught minus 1 over R naught is 1.5 minus 1 over R naught, so 0.5 over 1.5, that's 1/3. So we're vaccinating dogs at a rate of 1 in every, let's see, what is 1 divided by 1,800? I mean, all these inverses are confusing. So we have 1,800 days divided by 365. So every 5 years, like we said, the dog's life expectancy was 2.5 years. And so somehow, by vaccinating dogs on average every 5 years, we're eliminating it. So something does seem off. Wonder if our population turnover is too low, so that we're accumulating vaccinees too fast.
Vaccinated per yeah, what's the proportion of the population that's vaccinated at the end of the days?
For this 1,800-day version? So everybody's vaccinated. So, great. So, it might be that the population turnover is small. How much time do we have? We might be almost out.
2 minutes.
Okay. Okay, so let's wrap it up. And this is normal for this lecture, right? Okay, this is I'm not surprised that we can't figure out what's going on. We figured out a series of steps and debugged a lot of stuff in an hour and a half. And I'm going to post this, and we'll try to figure out what's going on and then let you guys know what's up. But the point is that this is how modeling works, right? So the goal of this is to make this seem like a tangible thing that you can play with and understand how the assumptions from the real world can be put down in code, and then you can run the code, look at it, figure out what you did that's wrong, which you always will make mistakes the first time, and then fiddle with it. But the only way we debug things in this was by understanding what the parameters meant in the real world, right? When we realized that we had each dog biting 100 dogs before it died, we knew that that was a problem, right? If we didn't have the biological understanding to go with it, it would have been very difficult. So modeling is really useful, again, in an exercise of like going from the real world, abstracting back to get to your research question, and this sort of back and forth. Yes?
Maybe we're going to end up
version control these, but some of the things we took out because we realized after some looking around that either we had a changing error or different error parameters. So I think we explored because we wanted to. Some of the things we wanted to remember earlier. Is there a suggested best practice? Because I'm not just holding back on top of it, but you know, if you didn't keep your data journal or whatever, you could easily forget in a few days. Well, you did, because you left the last one.
So if I wasn't doing this live, one of the things I would do is I'd make everything a much cleaner function. So I could always be running a function and just change the arguments. And I'd try to make it as complete as possible at the beginning and then make plots and use version control exactly like you said to... Sorry?
And also use sequences to vary.
Yeah, and make plots of the sensitivity analyses. Yeah, it's a good point. I mean, as you create this, it is good to save snapshots of it. So especially when you break something that was working and you want to figure out what went wrong, it's very useful for that. And Git, which we'll be talking about more on Monday, is really the best way to do that.
So at the end of a good decision, you say you use Git.
Or when you hit a bug, I'll often commit and say, there's this bug I'm working on, this is it, and then I have a freeze shot of that, and I can try to fix it, and I can always go back to it, but then you can also commit the fix as well. All right, we should break for tea.